Well, good day. My name is Bill Goebel. I'm here at Exeter in Pennsylvania in the United States, and today we're going to have a seminar on safety instrumented function verification. I'll be primarily talking about engineering tools, and in fact the engineering tool Excellentia, and we're going to talk about all the things one must do to do a SIF verification using the fundamental performance-based concepts in IEC 61511. My background is many years of automation system design. I was primarily in a research and development department, and I've been doing functional safety work now for about 15 years. I very much enjoy SIF verification work, and it's one of my key specialties. In terms of housekeeping today, I'd like everyone to realize that your microphones should be muted. If you have any problems, please go to the Q&A tab and type in a comment, and I can read those. If you have any questions, please type the question into the Q&A box and in text, and I will read the questions out loud and give you an answer. That way we can avoid audio problems that we've had in other seminars. But do not hesitate any time during the presentation today to type in a question. Exeter is a network of very experienced engineering personnel from around the world. We have offices in North America, Europe, Africa, Asia Pacific, subsidiary companies, and we have a pile of people who know and understand safety instrumented functions. Exeter offers a series of engineering tools for alarm management and many safety life cycle duties, and I'm proud to say that Exeter has developed a lot of expertise in functional safety. Exeter publishes many textbooks on safety and reliability, and I'm proud to say that someone from Exeter has authored or co-authored all the ISA bestsellers for automation safety and reliability. If you would like more information on any of these, don't hesitate to look on the Exeter website. Exeter Certification is a company that does product and system level and personnel certification. The company is based out of Geneva, Switzerland, and at this point Exeter has done more product certifications for the process industries than any other company. Now, I assume many of you are familiar with IEC 61511. That is a standard for the process industries for functional safety. There's two fundamental concepts. Follow a detailed engineering process to do your design. One of the reasons the standard wants you to do that is to eliminate design mistakes, and that's just common sense, decades-old concept. Have a written process, follow the process, include all the things in the process you need to find and correct mistakes. And our objective in that is to avoid what we call systematic faults. The other fundamental concept in 61511 is that designs are performance-based. Performance-based. What do you think that means? Intent here is that there are no rules. It's not what we call prescriptive. There's no specifics in the standard that say you must, for a pressure over for an overpressure safety function, you must use 3 transmitters, and you must vote them 2 out of 3, and you must have 3 valves, and double block and bleed, and you must use a TMR logic solver. No, no, no. There's none of that. The standard says you figure out how much safety you need, and then you do a calculation, a design verification, to make sure your design meets your need. That is performance-based system design. It's very exciting in a way because it allows for new technology, new ideas. It allows smart people to figure out better ways to do things. Problem is, you must do design verification, which is absolutely the subject of today's seminar. The safety life cycle is a series of steps taken during the analysis, design, and operation of the safety instrumented system. And in the middle, or some of the steps used, are steps for design verification. Here's a kind of a simple view of the safety life cycle. You figure out what can go wrong at the beginning. You figure out how bad it can be. Document what you want to do about it. And then verify that your design meets needs. And lastly, figure out how to keep it safe. That's a very simple view. Functional and logical regarding the safety life cycle. Now what we're going to talk about today is the green box, SIF verification. We know what is necessary. We know what is needed. We do a design and then figure out how well the design meets the need. At Exeter, we do this with various engineering tools. I use primarily the Excellentia tool. The Select tool does risk analysis and SIL selection. The SRS tool does the safety requirement specification. The Silver tool does the SIF verification. We also have tools that do proof test generation and import hazard analysis. The SRS cause and effect matrix tool allows you to generate both process SRS and design SRS. The whole package is called Excellentia Suite. Now, the SIF verification is a series of steps in the middle of the safety life cycle. A series of steps that start with the safety requirement specification. That's a document that says, what do we need? What are the safety functions? How safe does each need to be? We start in step number 8 by selecting the equipment. In step number 9, we must select the architecture. In step 10, we must determine how we are going to test the equipment. And then in step 11, we do calculations and verifications to make sure the design meets requirements. And if it doesn't, then we go back and either pick better equipment or add redundancy or change the way we're going to test it. You can iterate and optimize till you get the perfect design. And today we're going to talk about those SIF verification steps in detail and how they are supported by the tool. I'll just stop for a minute and say, does anybody have any questions yet? Please do not hesitate to type a question into your Q&A box. Design verification basically requires that we meet 3 barriers. I like to think of them as. There are 3 fundamental requirements. Number 1, we must meet a probability of failure on demand, PFD average, or we must meet we cannot exceed a maximum probability of failure. If we do, the design is not safe enough. Requirement number 2, we must meet architecture constraints. There are limitations built into the standard. There's certain redundancy required no matter what. And lastly, we must have equipment that's capable, meet SIL capability. Now, all three of these barriers must be met, and of course, if we have three different SIL levels achieved by these three different barriers, you know which one wins. Smallest number wins. What variables are involved in the design verification? Well, looking at the left of the screen, IEC 61508 capability of the equipment is a major determining factor in SIL capability. The equipment design and its internal diagnostics impact its failure modes and the ability to detect those failures, generating a metric called SFF. The SFF, in combination with the amount of redundancy in any given safety function design, determines the architecture constraint. The failure rates and the proof test frequencies and proof test effectiveness are the key variables in the probability of failure on demand. Now let's take a look at SIL capability first. Here's a chart from IEC 61511. And if you are designing equipment for the process sector, you can develop, and you're not developing new hardware devices, you can purchase equipment based on IEC 61508, or you can use a proven in use technique. Either of these methods, as specified in 61511, will determine the SIL capability. Now, I'd just like to add that when we select equipment to be used in a safety instrumented function, we need to justify that equipment based on a combination of application requirements and safety integrity requirements, and then document that justification. What do I mean by application requirements? Please make sure the equipment will perform all the needed functions. Is it rated for its expected environment? Are the materials compatible with expected process conditions? And are there any safety manual restrictions that would have a negative impact on your application? Given that a product will do a good job in your specific application, then you need to determine the SIL capability and justify the usage of this equipment in such a critical application by either buying equipment that has 61508 certification or doing your own certification in a method called prior use justification. 61508 certification is a process by which manufacturers typically demonstrate to very competent and technical companies, independent companies, that their product meets all the requirements of IEC 61508. The result is typically a certificate that looks like the one on the left of your screen. This particular certificate came from Exodus Certification. Exodus Certification has done about 60 projects now, typically more than, well, actually in the process industries, based on currently available equipment, Exodus has done more certifications than any other certification company in the world. Alternatively, you can use a prior use integrity justification. So you may wish to call the manufacturer, as I know that many certification projects are in progress right now. Save you a lot of work and documentation if you can get the certified product. But you don't have to. The standard does not require 61508 certified products are used. The Excellentia Silver tool does completely support SIL capability determination. When you bring up a silver screen, you may select whether you want to use the SIL capability in your analysis. The main reason that it gives you the option is that some companies prefer not to have this documented in their tools. but most companies prefer the automatic documentation of SIL capability provided by such tools. I guess my point is, why not use automatic documentation? And we'll show you more detail about how that works. There is a prior use report generator built into the Silver tool that asks you a number of questions and documents your particular self-certification process automatically and quickly. And that's one of the things I like to do when I'm out on a job. I like to quickly document my prior use justifications when I have them. See a question popped up. Let me just see if I can find them. First one, if a SIF must include non-IEC 601-508 elements, can Exida generic failure rates be used as an alternative to prior use? The simple answer is no. Exida failure rates are pieces of data. Pieces of data that are actually valuable to you, and you can certainly use Exida or any generic failure rate data. But that alone is not enough to justify prior use. You must also have your own records of prior use justification. Now, we do have a webinar on prior use justification that goes into a lot of detail on what is required. And there's another one scheduled coming up in the next few weeks. So if you have detailed questions about what you need in addition to failure rate data, do not hesitate to sign up for that web seminar. For those of you who can't make it, there is a recorded version of that on the Exida website. So the simple answer is you can absolutely use generic failure rate data. You don't have to calculate your own failure rate data, but failure rate data alone is not enough to complete a prior use justification. There's another question. When I played with this, when I have the box, I understand the question. I'm going to paraphrase a little bit. An Excellentia, or in particular a Silver user, checked and unchecked the SIL capability box, and the resulting SIL changed dramatically. And my first comment is yes, that's exactly what happens, and I will demonstrate to you why. And it is in fact important to justify the use of your equipment, and with Excellentia you can automatically document your justification. And I'll explain to you, I'll demonstrate that to you in a minute. Thank you both for those questions. The second thing that we need to worry about when doing SIL verification is, of course, the probability of failure. There's two metrics involved. Probability of failure on demand average. That's a metric for what's called a low demand application. Low demand means that a dangerous condition doesn't happen very often, and that in fact we're doing proof testing at least, well, more frequently than the dangerous condition is expected. And therefore we can take credit for proof testing. In high or continuous demand mode applications, there's a different set of numbers used, and it's basically probability of failure per hour. This is used commonly in machine safety, the automotive industry, but it's not that common in process industries. Of course, the Excellentia tool supports probability of failure calculations, and when you start up a Silver screen, there are a number of important measurements and variables that are requested. You can also, of course, in Silver, like any good probability calculation tool, you need to specify whether it's high demand or low demand, because the SIL can be very different. And proof proof test intervals, and many things depend on demand rate. So in the Excellentia Silver tool, you can either specify high demand, low demand, or you can actually enter the demand rate, and it'll automatically calculate and check for you. The third barrier is architecture constraints. There is a certain amount of minimum hardware fault tolerance. Or, I'd like to paraphrase, there's a certain minimum amount of redundancy required in certain situations. There is a table in 61511 with these minimum architecture, but quite frankly, it's more restrictive than the IEC 61508, and I find it to be so restrictive that it's not that useful. It's meant to be simple, but simple is conservative and restrictive. Fortunately, clause 11.4.5 of 61511 allows all of us to use the tables from 61508, where we're allowed to take credit for good engineering practices, including especially automatic diagnostics. Of course, any good SIF verification tool like the Excellentia Silver does support the architecture constraint, and in Silver you may pick whether you want to use the 61508 tables or the 61511 tables. In fact, in a tool like Excellentia, it's possible to even ignore the architecture constraints for those companies who do not wish to follow standard. Now, how does this all work? In the Excellentia tool, you simply enter in the parameters from your proposed design. Think about the sensor. You can have groups of sensors, and you can have multiple groups of sensors, and you can have voting between the groups. And it's very, very flexible. You can enter the number of groups, the voting between the groups, and the common cause between different groups. You can enter a quite complicated design, although quite frankly, most of the time the designs are simple. Once you figure out what the groups are for each group, you enter the group name, you can reuse the group, you can enter the group voting, you can have multiple sensors within a group and vote them differently, different types of redundancy, you can have different repair times, proof test intervals, and proof test coverages. Of course, the most important thing is you pick the sensor type and all the various parameters that go with it, including high trip or low trip, all the things that have a significant impact on the result. When you hit the Advanced Option button, you can actually go in and see the failure rates that are automatically assigned, if you wish, to the devices selected. And the fascinating thing is the database knows which components are 61508 certified. And the database knows the SIL capability of these components. For example, look on the line with the description sensor. We've selected a Rosemount 3051C, software revision 7 or above. That has a systematic capability of SIL 2 or SIL 3, depending on the level of redundancy. That's what I mean by automatic documentation. You don't have to go look it up, all this stuff, and document it. The machine does all that for you. Quite frankly, I like that very much because I'm not big on generating reports. I like to get my work done and let the machine do all the boring work, I call it. Of course, for any given design, we specify the logic solver. Is a general purpose PLC or an Emerson Delta V SIS or a Triconix Tricon. What is the average repair time, proof test intervals, and proof test coverages? Enter all that information. And lastly, we can either take advantage of either the automatic channel selection, which is very nice. If, for example, I have picked a Triconix Tricon, it knows that the analog input modules have 16 or perhaps 32 channels, depending on what kind of analog input module is used. It knows that when you pick a Rosemount transmitter, we need one analog input channel, and it automatically picks the number of analog input channels, the number of analog input modules, and takes care of a lot of details for you automatically. That's what I call that's the way an engineering tool should work, because it saves you time and increases probability of, or decreases probability of making a mistake. Just checking questions again. No, I don't see any new ones, but I'll just remind you again, please don't hesitate to type in a question. Lastly, for any safety instrumented function in the process industries, we need to type in all the information about the final element. You can type in the group name, for any given group, common cause factors, mean time to repair, proof test intervals, proof test coverages, the different types of equipment that's used, and there's open to trip, closed to trip, and all kinds of different options. If it's a remote actuated valve, for example, do you require tight shutoff, or is it in a severe service application? All of these things will have an impact on the failure rates of valves. When all that information is entered, and based on the parameters entered in the beginning, the safety instrumented function results are presented. Okay, so a question. Where do you get the group parameter from? A group is a collection of instruments. For example, if you have a remote actuated valve, a single remote actuated valve might consist of many different parts, like a solenoided actuator, a valve, a quick exhaust valve, and all the pneumatic controls. Think of all that. Think of that set equipment as 1 out of 1. But if you pipe up 2 of those valves, valve assemblies, such that you only need 1 to do the safety function, that's called 1 out of 2. So you could either call that one group with 2 valves with internal voting of 1 out of 2, or you could define that as 2 groups. Each group is 1 out of 1, and the voting between groups is 1 out of 2. The reason you would specify it as one way or the other is if you want different repair times and different parameters. The rest of the question is, where do I get the parameters from? The beta factors and MTTR. Well, MTTR, for example, is something you really have to estimate based on your own situation. Do you keep spare parts on hand? Are repair engineers available on a moment's notice, or do you have to call them in from somewhere else in the world? Think about all the things that affect repair time. Many people simply use a number like 72 hours to account for long weekends, or even 168 hours, which is 7 days, to account for spare parts being shipped in from a remote location. So basically, mean time to repair is a function of your particular site, your site repair policies, and site capabilities. The beta factors are a common cause factor, and Excellentia does have a questionnaire that you can fill out that will automatically estimate the beta factor for you. So I hope that answers your question. If it doesn't, please type again. Now, take a look at this chart. I know these numbers are a little bit small, but the SIF results on the right-hand side are what I'd like you to take a look at. For this particular design, the achieved safety integrity level is 0. Can you see that? Oh my goodness, this does not even meet SIL 1. Now, where's the problem? The probability of failure is 0. The architecture constraint is 1. The SIL capability is 0. So the architecture is not the problem. It's the probability of failure and the SIL capability. Now, let's look over to the left-hand side, down toward the bottom, and we'll see where the PFD is coming from. In this case, I can see right away by the big red section of the pie that the sensors are causing a lot of the problem. So we better go back and look at that part of the design first. I can also see in SIL capability that both the sensors and the final elements are sitting at 0. So I need to do a better job of picking either 61508 certified components or doing my prior use justification. Either way works. And of course, I can take a look at the detailed probability of failure calculation and look at PFD and PFD average as a function of time. Now, let me just show you some of this live. I'm going to switch over to the Excellentia tool. Okay, it looks like everybody could see it. As an example, in this particular safety function that I'm going to design, I am going to consider architecture constraints, and I'm going to use the 61508 tables. I am going to consider systematic capability. First thing I'm going to do, this is a nice simple design. I have a single sensor. So I'm going to pick a Rosemount 3051C, common, very popular pressure transmitter. I've got clean service. I do not have a remote seal. I don't have a problem with impulse line plugging. It's a high trip, and I'm setting the diagnostic alarm to under range. But I'm going to turn on diagnostic filtering. Okay, per good design practice, I'm going to pick a nice logic solver, Triconix Tricon, because everybody knows the PLC is typically where all the problem is, and you've got to spend money buying a good safety PLC. Haven't you ever heard the term, all you need for a SIL3 design? Or haven't you ever heard the phrase, all you need for a SIL3 design is a good SIL3 logic solver? Let's find out if that's true or not. So I've got a single Rosemount 3051C. I've got a Triconix Tricon, and I'm going to put in one valve assembly. I'm going to use a Fisher DVC 6000 to interface the Tricon to the actuator. Assume for the moment that we will activate the automatic partial stroke testing. I'm going to use a Fisher 1051 piston type actuator, and I'm not sure what kind of valve to use, so I'll just choose a generic trunnion mount ball valve. Close on trip. I do not need tight shutoff. There is no severe service. So for this set of equipment, for this particular design, let's check the results. Oh my design does not even meet SIL 1. What's the problem? Well, the PFD average meets a SIL 1. The architecture is not the problem. It meets SIL 1. It's systematic capability. So let's look down at the bottom of the screen. The sensor has a systematic capability, look over on the right-hand side, of 0. That's a problem. The logic solver has a 3. Well, of course, it's a good logic solver. The final element has a systematic capability of 0. Oh my goodness. What do we do about that? Well, let's go to the sensor first. We have a choice. We can either pick a safety certified sensor, or we can do a prior use justification. I'm going to go up and hit the Advanced Options button. One choice is we could do a prior use justification. So I'm going to go over to the Proven in Use button and hit the Proven in Use. And it says, do you wish to perform a Proven in Use justification? And if I say yes, I will go to the questionnaire, and I can answer my questions, and I can document the data that I keep, and I can document my manufacturer's auditing process and everything else I need to do a prior use justification. Say I'm doing a really good job on prior use justification, and I determine that the device capability is SIL 3. Better sign in. I did the work. Just type in my initials. Say OK. We want a description. Oh yes. We have to make sure that the application is the same as the application that we used it in is the same as the new application. We also need to track what's the design revision. Well, we're talking about revision 2.32. I got to go get that off the label plate. Am I done? Yes. Now I have documented a systematic capability of SIL 3. Job is finished. Now, alternatively, I could have. Let's go back and look at my final results. Now look at that. If you look in the bottom right-hand portion of the screen, hopefully you can see that the SIL capability for the sensor is now 3, but the final element is still 0. So we have a problem there. Let's go to the final element group. I'm going to, instead of picking this generic trunnion ball valve, I'm going to go pick a SIL certified Fisher Controls V-ball. Check my options. Now I see that the DVC 6000 is a SIL certified component. The Fisher Controls 1051, 1052 is a SIL certified component. And the V-ball is a SIL certified component. So I do not have to do a prior use justification. I'm going to hit the OK button, and let's go back and check results now. Look at that. The systematic capability has gone up to 2. The achieved safety integrity level has gone up to a 1. Where's the problem? Let's say I had to meet SIL 2. The problem is both in architecture constraints and in probability of failure. And I can see by looking at the pie chart, my final element is still a big problem. So I have to go back. I'm already using partial valve stroke testing. I'm closed to trip. I don't have any. I'm not sure I can do anything here except maybe use 2 valves. So I'm going to switch to a 1 out of 2. See what that did. You can see right away the valve is now fantastic. It's contributing only, 36%. The sensor is the problem right now. And I'm still having an architecture constraint problem. FD is okay. I've got a SIL 2 on that, but I can go in and, oh my. Easy way to solve that is I'm just going to pick the safety certified 3051C. It's a much better product and has much better diagnostics. So by picking the new safety certified pressure transmitter instead of the one I did the proven in use for, now I've got a nice clean SIL 3 design. Okay, I've got some questions here. the question is, what is the best frequency to use for partial stroke? And this is a debatable issue, but in my mind, if you take out all the emotion involved and just take a look, what I've told by the world's valve experts, including many different valve and actuator manufacturers, is that depending on the application, the materials and the process materials, what you'd like to do is stroke it as frequently as you can without wearing out the product. Let's assume that you're going to run for 10 years and you do a stroke every month. That's 12 strokes per year times 10 years, that's 120 strokes. Let's say that the valve is rated for 10,000 cycles. Well, you're not even close to wear out. So the first thing you have to check is wear out. You don't want to stroke it so fast that you're going to wear out the valve during the expected useful life. Usually that's not a problem at all. I know many of these actuators and valves are rated for like 100,000 or even 1,000,000 cycles. You could stroke every minute and not cause a problem. Many people pick a number like once a shift, once every 8 hours. Many people pick a number like once every day. The key is you don't want the product to sit there to the point where cold welding occurs between seals and metal. As I recall, the Parker O-ring handbook indicates that cold welding starts to occur in the period of 12 to 24 hours. Of course, that's a function of materials. I like to think of a situation where you stroke every day. Many people think that's crazy and use a number more like once a month because they are worried that a stroke will cause a false trip. You do have to make sure that's not a problem. In the particular product I chose, DVC 6000, the partial stroke pressure is limited. What you don't want is a partial stroke device where they take the pressure in the actuator all the way to 0 in order to get the valve to move. Because if it's stuck, you take the pressure to 0 and it might snap shut. So I like a product like a DVC 6000 where the minimum actuator pressure is specified and they do not take the pressure to 0. When you have a situation like that, you have really reduced the probability of a false trip and you can go with a higher stroking frequency. Okay, we have another question. For what type of voting application? What voting on groups should be used instead of voting on legs in one group? In the Excellentia tool, I generally go with voting between groups because most of the time the components within one group are tested and repaired at the same frequency. If you have some special problems, then and you must test at a different frequency, then you can vote between groups and specify the products as different groups, and the Excellentia tool will work perfectly. Questions now. This taken care of here for the moment. Okay, I'm going to go back to the Excellentia tool. I've just finished a reasonably good SIL2 design. I have a risk reduction factor of 463. It's a nice mid-range. I've got a lot of safety factor. You know, I might be able to increase the proof test intervals. Take a look at that later. If I needed a SIL3 design, I'm really going to have to take a look at the sensors, first of all. think I've got to have like a 1 out of 2, or maybe 1 out of 2 on the sensors would be a real good thing. See how that helped me. That's almost a SIL 3 design. I still have to go back and take a look at my valves right now. I'm going to have to do some detailed work because I've already got 2 valves. I've already got partial stroke testing, and the probability of failure of the final element is a bit too high. So what I have to do is go in and do some very detailed common cause analysis, see if I can reduce the beta number, and if I can't, then I simply must reduce the proof test interval, or find a... That's about it. So, point, SIL 3 is hard. SIL 2 is a lot easier. Main things I wanted to demonstrate are the tool automatically documents the architecture constraints, the SIL capability. The tool automatically knows which parts are certified and to what SIL level they are certified, and I like it because it just saves me a lot of work which I consider a bit boring. Let me double check the questions again. Okay, nothing new. All tools. One must have confidence in any tool used in the world of safety. So I just like to note that the Silver calculation engine, the tool used to generate the results, has been certified per 61508, and there is a certification report available from TÜV Nord. It can be used up to SIL 3. SIL 4, you need to do extra verifications. That's pretty good, though. To the best of my knowledge, no one else in the market has a good 61508 certification on the tool. I'd like to let you know that you can use an Excellentia tool in many different forms. It's available as an application service online in single-user or multi-user form. In other words, all you need on your machine is a browser. It's available as a standalone tool where you do not need an internet connection in single-user or multi-user forms. Site licenses are available to be installed on company servers, or an Excellentia server is available dedicated to your purposes. I see one new question. Good question. How is proof test coverage defined? Any particular proof test may or may not detect a dangerous failure in a product. The easiest example of that is, what if your proof test for a remote actuated valve was a full stroke? Would that test actually tell you if the valve sealed properly or not? No, it would not. A valve could do a full stroke, and it does tell you that the actuator works. It does tell you that there's no jamming on the valve stem. It certainly tells you a lot of things, but it does not tell you if the seat in the valve seals properly. So it's an imperfect proof test. Now, the way in which there is data available, in fact, in Excellentia, in the proof test generator add-on, plug-in it's called, where you can specify the proof test type, and the tool will give you the proof test coverage number. Those numbers are determined by detailed failure mode effect and diagnostic analysis work. And for those of you who would like a very detailed explanation of that, we do have a web seminar on mechanical FMEDA proof testing. Thank you for the question. Very good. There is training available for Excellentia. It can be at your site It could be in a public, local course. The courses are available in 1-day, 2-day, or 5-day. I'd like to let everyone know there is an Excellentia Users Group meeting coming up May 19th through the 21st in Houston, Texas. There is information available on the excellentia.com website and, of course, on the Exida website. Does anybody else have any questions about Excellentia? I was hoping today that you would see a little bit about what's involved in SIF verification. I was hoping today that you would see the 3 primary barriers: the probability, which is what everybody thinks about, the architecture constraint, and the SIL capability. All 3 are limitations in a design. And if you meet and document that you meet all 3 of these limitations, you have a clean, well-designed safety function. Now, there's a question. Is it a problem if other components of Excellentia are not independently certified? Like Select. In fact, you saw on the slide that the Silver calculation engine has been certified per 61508. For the most part, that is because it's really hard to do these calculations. They're very complicated, and it's really hard to do them by hand to verify that they were correct. Therefore, people at Exida, including myself, felt very strongly that that calculation engine needed to be 61508 certified. In the world of LOPA and SIL selection, it's easy to see the result of the calculation. For the most part, it's multiplying 2 numbers together. I always look at the results of my tools, and I make sure it always makes sense to me. It's hard to see, understand if the results of SIF verification make sense. It's easy to see that tools like Select make sense. And therefore, most people, in fact, no one has ever chosen to get other components certified. The software is developed per the same certified software development process, so it wouldn't be that hard, I suppose. But right now, there are no specific plans for the easy tools. Another question. Is the systematic capability we adjusted basically justifying the manufacturing quality process? Manufacturer's quality process is an important part of prior use justification. In our seminar on prior use justification, we talk about the level of depth required for SIL 1 versus SIL 2 versus SIL 3. At the end of the day, prior use justification means that you are taking responsibility for selecting that instrument. You sign your name and you say, I know this will work because I've audited the manufacturer, I have used this product for years, I have kept track of how well they've done in my application, and I know they're going to work. And I sign it off and say, I'm responsible. And so we did adjust the systematic capability because we were taking responsibility. And of course, that's something any end user must do. Another question, do you have software for HAZOP and SIL assignment? And the answer is yes. Actually, there's a new package coming out called SIL HAZOP. It is available today, and there's the PHA import tool. We'll take the results from SIL HAZOP as well as other HAZOP tools and bring them right into Excellentia. Take a look at the Excellentia website or the Exida.com website, and it'll give you lots of information on these other tools. Next question. excuse me, can I apply any voting, say 8 out of 8 groups? Not any voting. In fact, it depends. In terms of what I call X out of X, which is your 8 out of 8 example, it's very easy. You can take that number up. I believe you can take that number up as high as you want. I only recall going up to 6 out of 6. But as I recall, I can take that number up higher because the two numbers are the same. It does remind me that Excellentia definitely does not have voting for things like 2 out of 10 or 2 out of 18. And there's a very good reason for that. Although the logic in the logic solver may very well be configured to say trip when 2 out of 10 sensors trip. You have to ask yourself, why would anybody put in 10 sensors when 2 will work? The answer is, over and over again, I get this answer, well, guess 2 don't work. I need 10 sensors because any one sensor may not pick up the dangerous condition. This is commonly used in, for example, temperature applications where they're looking for over temperature spike across a large process vessel, polyethylene reactor. Must have been 100 temperature sensors, and if the temperature spiked in any one particular area, we would trip. That's not 2 out of 100. That's 1 out of 1. Unless all the sensors can detect the dangerous condition, the voting isn't the same for safety as it is logically. Please be careful about that sort of thing. I've seen a lot of people make big mistakes in their designs with general purpose SIF verification tools that allow you to do X out of M or M out of N, whatever you call it. But generally speaking, it's not real. Fire and gas sensors are in this category also. We have a paper on this specific subject on the Exida website. Please feel free to read it. Any other questions? Just scan and make sure I got them all. Thank you very much. We have recorded this session, and it will be available again on the Exida website. Lots of information is also available on the Exida website. Thank you very much for your attention. I hope you have received some useful information. If anybody has any further questions, do not hesitate to send an email. Thank you all for attending, and goodbye.